Let's begin by exploring an important concept about motion that often gets misunderstood. When we look at an object moving both horizontally and vertically at the same time, it might seem like gravity changes because of the sideways motion. However, gravity only affects vertical movement, no matter how fast the object moves sideways. This means the horizontal and vertical motions are actually happening independently, but at the same time. They don't influence each other. The diagram here shows how an object moves forward while falling straight down due to gravity, illustrating that these two motions occur simultaneously but in separate universes. This basic idea helps us understand more complex motion and sets the stage for what we'll discuss next. Let's take a closer look at the differences between what we call the horizontal and vertical universes in terms of motion. Horizontally, there's no accelerating force acting on an object, so the acceleration is zero in that direction. As a result, the velocity stays constant because nothing is pushing or pulling the object to speed it up or slow it down. On the other hand, vertically, gravity is the only accelerating force we deal with. This means the acceleration is a constant 9.8 meters per second squared downward. Due to this acceleration, the velocity in the vertical direction keeps changing as the object speeds up or slows down while moving under the influence of gravity alone. This contrast is fundamental to understanding how objects move in different directions. Here, we see an example of a horizontal launch where the object starts with an initial horizontal velocity but no vertical velocity. This means the object has no upward or downward motion at the moment of launch and begins its downward fall just like an object that's simply dropped straight down. In other words, the vertical velocity at the start is zero, so gravity immediately takes over to pull the object down while it continues moving horizontally at a constant speed. This sets up the classic projectile motion, where horizontal and vertical movements are independent of each other. Here we see the basic equations that describe the motion of an object launched horizontally. The horizontal distance traveled, x, is calculated by multiplying the horizontal velocity by time. Since there's no acceleration in the horizontal direction, that velocity remains constant. Meanwhile, the vertical drop, y, is determined by the acceleration due to gravity and the square of time, showing how far the object falls as it moves forward. These two equations together let us predict the path of the object as it travels through the air under these conditions. Here, we have a car positioned at the edge of a 50-meter-high platform, moving horizontally at 30 meters per second as it goes over the jump. Horizontally, we know the initial velocity, but we're trying to find out how far the car will travel before it lands. Vertically, the car starts with no initial vertical speed, and it's dropping from a height of 50 meters under the influence of gravity. The main question here is how long the car will be in the air during the fall, which will help us determine the horizontal distance it covers through the jump. This setup breaks the problem into horizontal and vertical parts for easier analysis. To figure out how long the car is in the air during its fall, we focus first on the vertical drop. The car falls 50 meters, and we use the formula for vertical motion under gravity to find the time it takes. We set the vertical position equal to negative 50 meters because it's falling downward, and apply the equation y equals half of gravity times time squared. Plugging in the numbers, we get minus 50 equals half of negative 9.8 times t squared, which simplifies to t squared being about 10.2. Taking the square root gives us a time of approximately 3.19 seconds. This time determines how long the car is falling, which is essential because we need it to calculate the horizontal distance traveled. Without this hang time, we can't solve for how far the car moves horizontally. So now that we know the car falls for just over 3 seconds, we can use that to find the horizontal range next. Now that we have the time of flight from the vertical drop, we can use it to find the horizontal distance traveled. Since horizontal velocity remains constant, we multiply it by the time to get the range. Here, the horizontal speed is 30 meters per second, and the time is 3.19 seconds, giving a horizontal distance of 95.7 meters. This approach breaks down the problem into two simple one-dimensional calculations, making it straightforward to solve. The vertical drop sets the timing, which is crucial before determining how far the object moves horizontally. When we launch an object at an angle, its velocity has both horizontal and vertical components. We can't just use the diagonal velocity as is in simple one-dimensional equations. Instead, we break it down into these two components using trigonometry. The horizontal velocity is found by multiplying the launch speed by the cosine of the angle, and the vertical velocity comes from the launch speed times the sine of the angle. This process is necessary to translate the initial diagonal motion into separate pure horizontal and vertical values that we can work with in our calculations. As we look at this trajectory, you can see how the horizontal velocity remains constant throughout the motion, unaffected by gravity. Meanwhile, the vertical velocity changes. We start with an upward direction, which slows down until it reaches zero at the peak, and then it reverses downward as gravity pulls the object back down. This shows how gravity only influences vertical movement, while horizontal motion stays steady. At the maximum height of a projectile's path, the vertical velocity is exactly zero. This is really important because it gives us a key piece of information to solve problems involving the maximum height. Since we know the vertical velocity at the peak is zero, we can use that as a fixed point to find other unknown values in our equations, making it much easier to calculate the highest point the projectile reaches. This concept acts like a shortcut or cheat code in physics, simplifying the process of analyzing projectile motion. Let's look at how we break down the motion of the tennis ball into horizontal and vertical components. The initial speed is 25 meters per second at a 40-degree angle. Using basic trigonometry, we can find the horizontal velocity, which is 25 times the cosine of 40 degrees, giving us about 19.1 meters per second. The vertical velocity is 25 times the sine of 40 degrees, which is roughly 16.1 meters per second. From here, we treat these motions separately. The horizontal motion moves at a constant velocity since there's no horizontal acceleration, while the vertical motion is affected by gravity, which is minus 9.8 meters per second squared. This way, we can analyze the ball's path as two one-dimensional motions running side by side. To find the total time the ball stays in the air, we start by recognizing that it begins and ends at the same height, so the net vertical displacement is zero. Using the equation for vertical displacement, y equals the initial vertical velocity times time minus half of gravitational acceleration times time squared, we set y to zero because the ball returns to its starting level. Substituting the initial vertical velocity as 16.1 meters per second, we get the equation 0 equals 16.1 times t minus 4.9 times t squared. Factoring out t gives us t multiplied by 16.1 minus 4.9t equals 0. Ignoring the trivial solution at t equals 0, we solve 16.1 minus 4.9t equals 0, resulting in t equal to approximately 3.28 seconds. This means the ball remains in the air for 3.28 seconds before landing. Next, we focus on finding the maximum height reached during the motion. To do this, we use the fact that at the highest point, the vertical velocity is zero. Starting with the kinematic equation relating velocity and displacement, we plug in the initial vertical velocity and gravitational acceleration. Setting the final vertical velocity to zero helps us solve for the maximum height. After rearranging and calculating, we find the height to be 13.2 meters. This step only considers the upward part of the motion, so we ignore the total flight time and concentrate on reaching this peak height, which serves as the absolute ceiling for the problem. Moving forward, let's focus on calculating the baseline range. Using the hang time of 3.28 seconds, we apply the formula for horizontal distance, which is speed multiplied by time. Here, the constant horizontal speed is 19.1 meters per second, so multiplying this by the total time of 3.28 seconds gives us a distance of 62.6 meters. This calculation shows the impact zone by determining how far the object travels horizontally during its hang time. Now, let's bring everything back together by combining the horizontal and vertical velocities to find the ball's final velocity at impact. We do this by treating the velocities as components of a single vector. By applying the Pythagorean theorem, we calculate the magnitude of the final velocity as the square root of the sum of the squares of the horizontal and vertical components. Substituting the values, we get a speed of 25 meters per second. The direction of this velocity is 40 degrees below the horizontal, showing the combined effect of the two components as one final trajectory. This step completes our understanding by merging the two separate motions into the actual path the ball follows at impact. Now, to understand the ball's final velocity at impact, we combine the horizontal and vertical components into one vector. The horizontal speed is 19.1 meters per second, and the vertical speed is negative 16.1 meters per second, indicating direction downwards. Using the Pythagorean theorem, we calculate the final speed by taking the square root of the sum of the squares of these components. This gives us a speed of 25 meters per second, moving at an angle of 40 degrees below the horizontal. This step shows how these two independent motions come together to give the true motion of the ball when it strikes.